This is the question that was given on the final at UC Riverside a few years ago, and we never done this question before in our AP Physics class, but we have done incline, the cars driving on inclines. So the question is pretty long. I'm gonna pause it, or you go ahead and pause it and read the question, and I'm gonna pause it as well. I'm gonna write everything that is given, and then when you unpause it, at first try to solve, because we're almost at the end of circular motion and we have seen more problems, enough problems for you to be able to solve. The student who shared this question with me, he solved this question on this final, and it was 25% of their grade, and only he said that about 10-15% of students who solved this question in the classroom. So that means only 10-15% of students got higher than 75% in the classroom on their final. So go ahead, pause it, try to write everything that is given, and see from what we learned so far, can you solve this question? So here's the information that is given about the masses, and I'm gonna draw the forces acting on the masses. So I will have this force is mg, and there is tension force. And because the little mass is not moving up and down, then your tension force is equal to mg, or tension minus mg is equal to 0 because there's no acceleration. So the net force is equal to 0. The force is acting on the capital M, the rotating mass. So you have the normal force, you have mg, and if we say minimum friction, then the minimum speed that I have to calculate, the minimum speed, then the friction is going to be up. And if I say it's the maximum speed is moving at, then the friction has to be down, because with the minimum speed, the mass will want to move down, so the friction is going to be up. So here is the friction. There will be acceleration toward the center. So acceleration is centripetal acceleration, but I don't have to, on my free body diagrams, I do not put my acceleration, I only put the forces. And also there is tension right there. Then because my acceleration horizontal aligned with x-axis, then I'm gonna do the projections of the other forces to figure out the components, the vertical and horizontal. So this will be vertical component of n, and this will be horizontal component of n. This will be horizontal component of friction. This will be vertical component of friction. Then this will be vertical component of tension, and this will be horizontal component of tension. For the angles, it's easy. So this one is the same as theta angle. So this is theta, and that one is theta for tension. And the same for this angle. You see two vertical lines, and the friction line is passing through both of them. So that makes those two angles equal to each other. And then the one that is with the normal is a little bit more confusing. So I'm going to redraw the normal. So here is your normal force. And if I drop the vertical here, that will give me theta. That means this one is 90 minus theta, and this one is right angle. Now, if I do it this way, from this big triangle, this would be the right angle where n is. Then this would be 90 minus theta, and this angle would become theta. So your theta in my free body diagram is the right angle on the top. Now for F net is equal to MA, I have vertical forces acting on the mass that is rotating in a circular motion. N sine positive. So I have n sine theta positive. And then I have friction cosine positive, and I have tension cosine negative. And I also have negative mg, but I'm going to move mg to the other side because there's no acceleration. It's going to be equal to 0. So I can say minus mg equals to 0, or I can say equals to mg. For horizontal forces, my positive direction is with the acceleration, so I have n cosine aligned with the direction of the acceleration. I have positive t sine, and I have horizontal negative f sine theta, and equals to mac, because in this case we have centripetal acceleration. Also, your tension is equal to mg, so I could replace my tension with mg. Let me squeeze it right here. So tension cosine will become mg cosine. So this is mg cosine theta. And the bottom one, tension sine, will become mg sine. So plus mg sine theta. I also noticed that I plug in the lowercase m, but the mass that is rotating is the capital M, not lowercase m. So this is what I should have had. So now I'm going to replace friction with, so friction is equal to mu times n, and I'm going to replace friction is equal to mu times n, and move my third term, so this term, the one that is mg cosine and mg sine, to the other side of the equal sign. So I'm going to rewrite this equation with, instead of friction, I'm going to have mu times n. So here what I have, I moved that last term on the left side to the right side, and I replaced my friction with mu times n and mu times n. And because both of these guys have n, I can factor out n from both equations. So I took n out from the left side, both terms, and then now I can use that trick that you have seen me doing a few times in the classroom. Eliminate the n's because it's one of the unknowns. So I'm going to eliminate it by dividing both sides by each other. So I'm going to cancel these guys. And my final equation is going to look like, so this is my final equation. And now because the lowercase m, the mass that is hanging, given 1 kilogram, the uppercase m, the one that is rotating, is 2 kilogram. Radius, we don't need radius yet. Degrees is 70 degrees for theta, but make sure your calculator is in degrees. And mu is 0.4. So now I'm going to plug in my numbers and figure out what AC is equal to. So I got my AC is equal to 4.33 meters per second squared. And now your AC is equal to V squared over R. And R is given 1 meter. So that means V squared is equal to 433. Then V is equal to the square root of that, which is 2.08 meters per second. So this is the minimum, we solve for the minimum part, velocity at which the block can rotate in some circular motion and not slip down. And if you had this same question, so we solved for the minimum, so I did the B part, and for the maximum, your friction would change the direction. So instead of the positive sign right here, you would have negative, and instead of the negative sign right here, you would have positive, and the solution would be the same. But that was the final exam question at UC Riverside a few years ago, and was worth 25% of their grade, and only 10% of students solved it in the classroom. Here's another problem that I want to solve with you in this video. An object takes 2.4 seconds to fall 5 meters on a certain planet. Find the acceleration due to gravity on that planet and find the planet's mass if the radius of the planet is given. So we know the time it takes, we know the distance, and we know the radius of that planet. So I know the formula that the force of gravity is equal to G mm over r squared. And if G is universal constant and r is the radius of planet and m is the mass of the planet, then all of this can be replaced with little g, acceleration due to gravity, times m. So acceleration due to gravity on our planet is 10 because universal constant is 6.7 10 to the negative 11. Mass of the planet is given Earth. Radius of the planet of Earth is known. So we can calculate the acceleration due to gravity. It does vary a little bit here and there in different parts of Earth and how far you are from the center of the Earth in the mountains. But we're always rounded till 10. So if I know that it takes 2.4 seconds and 5 meters, I can find average velocity. So the average velocity in this case is going to be equal to the distance over time, which is 5 over 2.4, gives me 2.08 meters per second. If the initial velocity is 0, I can find the final velocity because average velocity is equal to initial plus the final divided by 2. Then your final velocity is equal to twice the average velocity, which is 416. So the final velocity of an object when it traveled 5 meters was 416. Then I can find acceleration due to gravity is the change of the velocity over the time it took. So that is 416 minus 0 divided by 2.4 seconds. So the acceleration due to gravity on that planet, 1.73 meters per second squared. So since I know that that is G, I'm going to use this G and plug it into my G formula. So your G is this part of the equation. So I know G is 173. Gravitational acceleration constant is 6.7 10 to the negative 11. Mass we're looking for, and the radius they said is 250 kilo means 10 to the third squared. So the mass of the planet is equal to 7.12 10 to the 23 kilogram. So that would be the mass of that planet that they're talking about. Here's one more question we're going to do in this video today. And the question is pretty long, so I'm going to let you read, pause it, and take time to read and understand what is asked. And then we're going to look at it together and try to solve it together. So what we have is the mass of the bead is given, the radius of the curvature is given, and they say that equilibrium length of the spring is 0. So that means when it is stretched to R, it will have some potential energy, but when it's released, its length is going to be equal to 0. And then we want to calculate the speed of the bead at the bottom of the loop if first the spring is attached to the bottom. So if the spring is all the way at the top, it has potential energy. So the potential energy of the spring, gravitational potential energy, and it has gravitational, and it has potential energy of the spring at that point. There is no velocity at that point because they say moving with the negligible speed. So they say with a negligible speed. And then it will convert into the kinetic energy of the bead at the bottom. So what I can write is mg, and the height that it is at is 2r plus 1/2 k and your stretch is 2r squared is equal to 1/2 m, and the velocity of it at the bottom. So I'm going to times all of them. Let's simplify. So what we have here is 2rgm plus, if I square 2r, I get 4r squared, and 1/2 of it gives me 2r squared k, and that gives you 1/2 mv squared. Then times all of them by 2, so I have 4rgm plus 4r squared k, and I'm dividing all of them by m as well, so I can solve for velocity. Divide all of them by m, and that will give you velocity squared, but if I take square root of both sides, then I get actually the velocity. So that answers your question at first, or you actually can simplify it. So you can divide by m one term and the other term. So if you divide the first term by m, you get 4rg, and then you can divide the second term, you get 4r squared k over m. So that would be the velocity in case the spring is attached to the bottom. If the spring is not attached to the bottom, so this was for A. For B, if the spring is not attached to the bottom, then you only have gravitational force. You don't have the spring force because the spring is not attached to the bottom. So what you have is mg2r is equal to 1/2 mv squared at the bottom. The m and m can be cancelled, and v is going to be equal to the square root of 4rg, or v is equal to 2 square roots of rg. So that would be the answer for the second one, when the spring is not attached to the bottom of the loop. Here's another question that is interesting, and I wanted to look with you at. A particle P moves around this circle with a radius r, as shown under the influence of a radial force of magnitude F. What is the work done by the radial force as the particle moves from position 1 to position 2, halfway around the circle? So I'm going to write the formula work first. The work is equal to the force times the distance, and then cosine theta. And that's the angle between the direction that it moves and the force acting. So if the particle moves from point 1, the direction in which the particle is moving is forward, but the force acting on it is toward the center. So you see that the angle is 90 degrees. And if I plug in 90 degrees into my formula, I will see that the cosine of 90 degrees is 0, and the work is done, in this case, 0 joules. It's a tricky question. Here's one more question. A satellite circles a planet Roton every 2.8 hours. So I'm going to write the period is 2.8 hours. But if I times it by how many seconds, it is 3,600 seconds in 1 hour. That gives me 10,080 seconds. And the orbit having a radius of, so the radius of rotation is 1.2 10 to the 7 meters. And the radius of Roton, so the radius of Roton is 5 10 to the 6 meters. What is the magnitude of the free fall acceleration on the surface of Roton? So I can start with the force of gravity is equal to gmm over r squared, and equals to the centripetal force. And the centripetal force is mv squared over r. So that is the centripetal force. So I can look at these two, and I will cancel m. Then I'm gonna solve it for the mass of the planet Roton. So the mass is gonna be equal to, I also could cancel one of the r's. So the mass is gonna be equal to v squared over v squared times r over g. And v is equal to 2 pi r, the distance, divided by the time it takes. So if I square my v, I get m is equal to v squared gives me 4 pi squared r squared times r divided by g, but my 4 squared, pi squared, and r squared has to be divided by t squared because I square the whole v. So that will give me 4 pi squared, that one is squared, cubed, and t squared g, Kepler's law. So now I'm going to plug in and find out what the mass of the Roton is equal to. So I got the mass of Roton equals to 110 to the 25th kilogram. And from the force of gravity, gmm over r squared. Sometimes we write the force of gravity as mg. And they ask you to find acceleration due to gravity on the planet of Roton. So this part is going to be the acceleration due to gravity, with the mass of the Roton that we just found and the radius of the Roton. And the radius of the Roton is the one that they give you, 510 to the 6. So now I'm going to plug in my numbers and find the acceleration due to gravity on that planet, or on the Roton. So I have g, which is 6.7, 10 to the negative 11. The mass I found 10 to the 25th. And divided by the radius of the Roton is 5 10 to the 6 squared. And that will give me 26.8 meters per second squared. All these formulas and problems involving Kepler's law are usually the ones that are with very complicated numbers that you have to plug in, but the problem itself is not as complicated. So what you needed to do is to find the mass of the Roton in this question, and then since the radius of the Roton is already given and the mass of the Roton you can find acceleration due to gravity on the planet Roton by understanding that the force of gravity formula already has acceleration due to gravity in it. Here's the last question probably that we're going to do in this video. Two stars of mass m and 6m are separated by the distance d. Determine the distance measured from m to a point at which the net gravitational force on a third mass would be 0. Let's say we have the mass m over here and the mass 2m over here, 6m. So I have 6m, I have m, and I'm going to call the distance between them, d. And I'm going to call this point is where another mass, and I'm going to call it like little m maybe. And the force acting on it is equal to 0. That means the force acting this way is exactly the same as the force acting this way. So this distance right here to this mass, I'm going to call it x. And this distance is d minus x. So this force and this force are both equal to each other. So the force on the left is equal to g m, the little m, over x squared, and that must be equal to g 6m m over d minus x squared. So I use the gravitational formula for both forces. And since they're equal to each other, I don't need this force anymore. I can cancel m, and I can cancel little m and little m, or lowercase m, the mass that we're looking at, some third mass, I can cancel universal gravitational constant from both sides. So what I get is 1 over x squared is equal to 6 over d minus x, and all of it squared. Cross multiply them, and you're going to get 6x squared is equal to d minus x squared, all of it squared. So if I use the formula for d minus x squared, which is d squared minus 2 times their product plus x squared, and equals to 6x squared. And d is given, and I'm solving for x, which is the distance. I'm looking for x. And if I move x squared to the other side, I have 5x squared. I'm going to move 2dx to the other side, so I will have 2dx, and minus d squared is equal to 0. And now I'm going to use quadratic equation to solve for x. X is equal to the opposite of b, so I have a. Let me just write it in different colors maybe. So this is my a, this is my b, and this is my c. So it's the opposite of b plus minus the square root of b squared minus 4a c squared, which is negative d, so it gives me positive d squared, over 2 times a. So x is equal to negative 2d plus minus the square root of, and I have 24d squared divided by 10. So x is equal to negative 2d plus minus the square root of d squared is d, and the square root of 24 is 4.9 divided by 10. So if I subtract, then I'm going to get a negative distance, and I don't want to have my negative distance. So I'm going to add them, and I'm going to get the answer. 4.9 minus 2 gives me 2.9d over 10, or 0.29d. So the distance is 0.29d, which would be the choice if it was a multiple choice question. This last question is a very common type of questions that you usually see on your AP exams for multiple choice questions, or you see in our final exams for multiple choice questions. But this will be concluding our video lesson for today. So follow the directions in the description and follow to the next video. So there's next video or the previous video that you haven't watched maybe, and I'll see you in the next video. Thank you for watching this one.